We're going to do is we're going to start to understand what we mean when we say a definite integral. So what is a definite integral? So to answer that question, let's review what it is that we've previously done, and let's see how we can talk about a definite integral. So before, we've been talking about approximating the area underneath this curve using Riemann sums, right? So let's just do this in the general case. So I have some function here, f of x, that's blue. And let's say I take this interval from a to b, right? And I want to use n rectangles. So n rectangles, maybe it would look like this. And again, I'm just approximating. So here's n rectangles. And what I want to do is I want to find what the Riemann sum looks like using summation notation. Because when I use summation notation, then I can immediately pass to the definite integral and what that means. So let's see. So here's n rectangles, okay? It's not exactly n rectangles, but let's just imagine that these are n rectangles here. Well, what does the area underneath the curve look like? Well, what does that look like? It looks like f of, let's say this is xi, x1, let's say. So f of x1 is the height of the first rectangle times delta x is this here, where delta x is b minus a over n, where there's n rectangles. Plus, the next one is going to be f of x sub 2 times delta x plus f of x sub 3 delta x, and I'm going to keep going with this, right, where I'm summing each one of these rectangles until I eventually get to, and I'm going to put dot 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 f of x sub n times delta x. And to write this as a sum, we should see that it's going to go from I starts off, or k, or whatever you want to use. I starts off as 1, and it goes all the way to n of x, f of x sub n. Sub I apologize, sub I, because I is changing from 1 to n delta x. And that is just a way to rewrite this sum, right? Because what does I start off as? I starts off as 1, and then it goes to 2, 3, 4, 5, all the way up to n. And that's just the way we talk. That's just summation notation. Now, the key here is that we need to see that the more rectangles I take, the better the approximation. So more subdivisions or rectangles, same thing, subdivisions, rectangles, more subdivisions, right? N, if n gets larger, more subdivisions, the better the approximation is. And that might take some time to convince yourself of, but basically you should just see that like this is going to be like more accurate to where the curve is. It's going to fit the curve better. The more rectangles you use, the more subdivisions are. There's just more precision, right? So this is key to see this geometrical fact, right? And what happens is the way we define this integral, this definite integral from a to b, is essentially just saying that we let n go to infinity here. We take the limit as n goes to infinity of this sum. I goes from 1 to n of f of x sub I delta x. And this here is essentially the definite integral. And we can say that this equals from, you draw out that long elongated s, you go from your lower limit a to the upper limit b of this curve is f of x, right? So you could kind of see how everything pieces out. Dx. So how does this relate? What is this? What's happening here? So this is the definite integral from a to b of f of x, and essentially f of x matches the f of x sub I. The delta x matches the dx here. And this sum, this integral sum, matches this infinite part, this infinite sum, this limit as n goes to infinity. So everything, you see, so this becomes like this becomes the f of x, and then the delta x becomes the dx. And this is your definite integral, and it just represents the area underneath the curve from A to B. Okay, it's exact, because the limit as n goes to infinity is going to be infinitely precise. It's going to fit the curve perfectly.